Hi! Episode 7 of Crash Course Physics revolved around circular motion. Get it? Revolved around? Huh? Anyone? Anyway, the central result was the formula for centripetal acceleration, A equals v squared over r. Or was it the result really? Because no explanation was given as to where this formula comes from, what kind of story lies behind it. When Sheeny mentioned that it can be found using derivatives, she probably had a calculation in mind close to what Matt Parker presented in his video a while ago. Here I want to show you a simpler way. The key is to note that in a uniform circular motion, the velocity vector also describes a circle when always drawn from the same base point. Such a diagram is called a hodograph. The acceleration vector then is tangent to the velocity's curve, being its derivative. In the original picture, velocity is total distance over time, so the circumference divided by the period. But in the hodograph, the exact same relationship holds for acceleration. It is the total change in velocity, the circumference of the velocity circle, divided by the period. Now both formulas contain the same prefactor, 2 pi over t, which means we can write the proportion v to r equals a to v. Solve for acceleration and there you go. A equals v squared over r. Let's take a closer look at this result to get a better appreciation of it. First, increasing the radius while maintaining v constant results in small acceleration. This is because the circular orbit becomes longer and thus the period, since we draw out this longer orbit, is still at the same velocity. But then we have more time to spin the velocity vector around once, so acceleration becomes smaller. That is the meaning of the divided by r part of the formula. On the other hand, let's now imagine v increasing while r remains constant, so we move around the same orbit at a faster pace. Not only does this lengthen the circumference of the velocity circle, but it also gives us less time to traverse it, as the period decreases with increasing speed. So the acceleration must become larger in accordance with both of these effects. More precisely, remember that acceleration is change in velocity over time. In our case, that is the velocity circle's circumference divided by the period. The circumference is proportional to v, but the period is actually inversely proportional to v. As a result, a increases as the square of velocity. Finally, we can argue geometrically from first principles by looking at the changes in a small amount of time delta t. The change in position is approximately v times delta t, while the change in velocity is approximately a times delta t. The two triangles are actually similar to each other, so their legs aren't proportional to each other, giving us the same proportion mentioned earlier. If you enjoy these nitpicks and want to follow Crash Course Physics along with me, don't forget to subscribe. See you next week.